All right. Good morning and good afternoon, everyone. My name is Tony Huang. I'm in charge of the most power division within Diodes. I'd like to share with you our perspective on the WBG and power modules. The background is I think the energy. The electrical energy is superior to other energies. So we see the growth of electrical energy faster. About last year, it grew about 5%, a lot faster than our population. So this is a little bit alarming. So we think the energy efficiency becomes very critical in the future. And so if we consider the same power, if we use a high voltage operation, it will help us reduce the conduction loss and material costs. So that's why WBG semiconductor is very important. It works in the high voltage operation and help to improve the power efficiency. And we also look into the power modules that improves the power density as well. It's optimizing the thermal dissipation and reducing the conduction loss and reduce the stray inductance. So what is a wide bandgap semiconductor? A wide bandgap semiconductor are the material that with larger bandgap voltage compared to the silicon. So you can see the energy bandgap for GaN and silicon carbide. They are about 3 times of silicon, and also the breakdown electric field for GaN and silicon carbide are almost 10 times of silicon. And also the thermal conductivity for silicon carbide is about 3 times of regular silicon. And from this perspective, GaN is slightly inferior, but it's comparable. So for the wide bandgap material, it has a higher breakdown voltage and a higher operating frequency and superior heat dissipation. And we see this smaller RDS-on variation across the temperature. So it's preferred for these applications. So from the application topology, you can see the silicon is still covering the biggest range of operation, but it's less efficient in high voltage and high frequency application. So that's where the WBG material comes in. And for GaN, GaN has a better switching frequency and but slightly inferior thermal conductivity. So it is more popular in the high switching loss application and more popular in the lower power application. For silicon carbide, it has a better thermal conductivity and the better capability for higher voltage application. So it is more popular in this area. So on the market forecast, GaN, I think our speakers has mentioned this, GaN has been quite popular for the USB PD chargers. Almost all the premium chargers these days are using GaN devices because of better power efficiency and better power density. And I think in the future, we'll see more and more telecom 5G and servers using lower voltage GaN for 100 volt and 200 volt application because of better efficiency than silicon. Also, I think from this prediction, the GaN devices will show up in the automotive in the future too. And silicon carbide is already very popular in EV. We see Tesla Model 3 using silicon carbide already. And also silicon carbide is popular in the renewable energy and the industrial application. So we see the growth rate continues more than 20% in the future. So besides wide bandgap semiconductor, more efficient power packaging are also critical. So from diodes, we try to move beyond the power discrete package to modules. So we partner with a company in Taiwan to launch power module manufacturing. And our initial focus is on the BSG, micro EV traction motors, inverters, using the regular silicon MOSFET first. And with the same production, we will move on to silicon carbide in the future. So as you can see, the on the right-hand side, for the right-hand side is for the regular MOSFET and micro HEV application. So you have a regular MOSFET in the power module, and at the bottom you see typical application for the silicon carbide power modules. So our focus for power module will be using based on the sintering system to achieve better thermal dissipation. So this theory of sintering is based on the atomic diffusion to build a metal bulk for better thermal and electrical conductivity. Right now, AG sintering is more popular. And also there are copper sintering now in development also. So you can see the thermal conductivity is much better than solder in this chart. So we apply those to the power module. We can see about 30% better power density or better power efficiencies for the silicon and for both silicon and for silicon carbide as well. Our silicon MOSFET, silicon carbide MOSFET application focus because of silicon carbide MOSFET has better efficiency than IGBT and a better lower system cost because of thermal is much better. You don't need a water cooling system. So also less CO2 emission. So our target silicon carbide application would be focusing on the traction motor, inverter, and onboard charger, and DC-DC converter. Currently, the silicon carbide suppliers are mostly focused on from the IDMs, including Wolfspeed and Infineon and ST Micro. So we think there's still rooms for us to go in. Here's an example of our silicon carbide application. We used the silicon carbide devices in the PFC application, and although our RDS(on) is higher, but we get similar efficiency as the competitors. Also, for the GaN market, we know there are two categories of GaN application solutions. One is enhanced mode, like the GaN from Navitas, enhanced mode devices, and also there are depletion mode GaN that requires additional low VMOS to work in a cascade configuration. And most of the suppliers are not IDM, so the wafers coming from the third party, like TSMC and also like from FPCL or other companies. We are looking into this market. We are working with third party as well in this application. For the GaN application, one of the case we use our lateral DMOS in cascade configuration with depletion mode MOS. We can see the efficiency is better than super junction devices, especially in the light load situation, because in the light load application, the switching losses is more. If we put this GaN into our AC/DC groups application, then the overall efficiency is similar to the bottom table.